All right. Hello, everybody. Welcome to your notes on magnetism. This should be pretty exciting. Please follow along with your guided notes. There will be things for you to fill in. Feel free to pause or rewind the video to think or draw or practice. Take this at your own pace. If you have questions, I am here. Please ask them. If you want to know more about something, I am here. Please ask. So let's get started. Now, we've all seen a compass before. Now, compasses are the first practical use of a magnet. Compasses are essentially these little small floating magnets on a needle. They're floating on water. They could be floating on oil. They appear to have been invented independently in China around 1100. And in Europe later in the same century, and they absolutely revolutionized seafaring. Before the introduction of the compass, geographical position and direction at sea were mainly determined by looking at landmarks, things you could see with your eyes from your boat, sometimes supplemented by looking at the stars or the planets that you could see. Other techniques include sampling sea mud from the seafloor, analyzing the flight paths of birds, observing wind, sea debris, the sea state. But again, all these things are unpredictable. Maybe it's cloudy and you can't see the sky, or you're too far to be able to see anything on land or to reach the bottom of the ocean. Again, once you get far enough away from land, a lot of these things become not helpful. I mean, the Vikings may have used some, what are they called, crystals to help navigate, to determine the sun's direction and elevation due to the polarization of light. And that's why they were very successful seafarers. But for the most part, this was not a great thing to stray too far from land. But now with compasses, a reliable way to orient yourself in space when you're in the middle of a bunch of water, really helped to increase the safety of navigating far away from land, which increased sea trade and definitely contributed to the age of discovery. Now, magnets are not just for compasses. They're everywhere to sustain our modern conveniences. They help us to generate electricity. They run electric motors. They help in the operations of appliances like telephones and radios. I mean, we know our refrigerator doors have magnets, but did you know they're also in speakers and headphones? We use them for magnetic locks that hold different things closed, but they're also on credit card strips. They're used to help for charging. They're on hard drives. MRI scanners use magnets. They're even used for maglev trains, induction cookers, and a lot of other things that I'm not going to name right now. So, I want to talk a little bit about dipolarity. We talked a little bit about dipoles when it came to point charges, but magnets also have the quality of being dipolar, meaning having two opposite sides. Magnetite is a form of iron ore, and it was given its name by the Greek philosopher Thales, who had obtained samples from a deposit near the town of Magnesia in Asia Minor. Much later, any piece of magnetized rock would be called a lodestone, lode meaning coarse, because of its value in giving direction. So basically, if you took one of these lodestones and tied it to a string and hung it from the ceiling and twisted it, and then released it, it would swing back and forth, and eventually their ends would end up in their original position, one pointing north, the other pointing south. Now you can do that as many times as you like, and consistently the north side would face north and the south side would face south. So we would call the north side, the part that was seeking the North Pole, we'd call it the north seeking pole or the North Pole. And the one that keeps pointing in the southerly direction, we would call it the south seeking pole or simply the South Pole. So the question is, why does this happen? Well, the simplest reason the lodestone finds north and south is that a force, there must be some kind of force originating somewhere in the North Pole attracts one end, while a force originating somewhere near the South Pole attracts the other end. right? We know that if there's going to be some kind of control across distances, there's going to need to be some sort of force or a field that creates that force or carries or transmits that force. So this explanation is an approximation, kind of an average description about what happens over the course of the whole Earth, because actually different places on Earth exhibit local magnetized attractions that differ from the global average. For example, if you were in Chicago and you used a compass, it would point directly north. However, if you were in New York, it would point about 15 degrees west of north. And if you're in San Francisco, it would do about 20 degrees east of north. This really freaked Columbus out back in the day because he didn't understand why his compass was not always as predictable as it should be. The good part is now we do know why that is the case. So today we know why north on a compass might be a little bit off. And the reason is there are many convection and density currents within the Earth's core and mantle that make individual magnetic fields of varying strength. And when these fields interact with each other and complement or oppose each other, they combine to produce a general magnetic field that does not necessarily coincide with the geographic poles. So instead, each magnetic pole is about 1,200 miles from its geographic pole. And it's not fixed there. The North Magnetic Pole actually lies in the Canadian North off the coast of Ellesmere Island. And as the currents in the core shift, the magnetic pole actually drifts northwest around the Canadian Arctic at approximately 35 kilometers per year. The South Magnetic Pole is pretty static, staying in position right around the coast of Antarctica. So now I'd love to show you what Neil deGrasse Tyson has to say about all this. He's got some pretty interesting stuff. So buckle up, no notes to take at this moment.
Hey, Chuck.
Hey, what's happening, Neil?
I'm back in your face.
That's right. Which means that we're gonna find out about something, hopefully that is delightfully obscure.
Obscure, but
Yes.
But the hope part is it will be obscure. The hope is that it's nonetheless interesting.
Yeah. Well, that's
This is
so
what
far, so good.
It's going good. All right, so I want to talk about Earth's magnetic field,
All right, already you got me.
if I may.
Yeah, this is good stuff already.
Okay, so we all know it has a magnetic field, and you learn that as a child when you have a compass, right? Particularly if you were in one of the Scouts programs, you have a compass, and the needle points north, and so that's north. Okay, so the north side of the needle points north, and that's how you know it's north. So let me start out by saying we all know that in magnetic fields, opposites attract, right? You knew this.
Yes. Well, you take the north and the north, you put them together, and it's very cool because
They repel.
yeah, and then you have magnet races. This is how you have magnet
You
races.
push them across the table.
Yes, you push them across the table, and that's how you have a magnet
Okay,
race.
so if you flip it around, then the north sticks to the south. Okay.
right.
So what that means is, if the needle on your compass is magnetized north, then it's actually pointing to the Earth's south magnetic pole.
Right. That makes sense because
It
that would be
means
the
what
opposite.
you calling the
of
North Pole is
It's
actually
not.
the South Pole.
Right.
I just want to start there.
Wow.
Okay.
Okay. Thanks for ruining everything. And now I don't know what to believe.
Okay.
Period.
Right. Earth's south magnetic pole is in the north because all north magnetic poles point to it.
Right.
Okay.
Interesting.
So I just didn't know if you knew that.
You
Put
know
that out
what?
there. And
I
don't
know
shoot
it-
the messenger.
I
Ain't
know
my
it
fault.
now, and I gotta tell you, I wish I didn't.
Okay, so
No,
but
that's actually very cool.
But wait, there's more.
Uh-oh.
Okay, so Earth's magnetic field is not aligned with Earth's rotation axis. Okay, so Santa Claus is up there on the North Pole, all right? And your compass doesn't actually point to him, okay? Well, it does point to him if you're exactly on the longitude where the North Magnetic Pole is found. If you are anywhere else, you are not pointing to the top of Earth's rotation axis. You are pointing to someplace in northwest Canada. Because our magnetic pole is tipped relative to our, what we call the geographic pole.
Okay, so the geographic pole, so the Earth sits, if you ran the pole, an actual pole through it,
If you did
sits
that.
on this tilted axis.
It's tilted, that's correct.
It's tilted.
And it's tilted by a lot. So a compass sort of points north, sort of. And by the way, I in the scout manuals, when
And
they talk
this
about
is the
use of-
device we use to find our way when we're lost.
well, you'll find your way.
You know,
to
you're sort of going the right way.
kind of, sort of,
Kind of, sort of. It's like getting directions in the hood, you know? Now, see, what you want to do here, man, what you want to do, you want to go straight down, right? You
Go
wanna
straight,
keep going.
and then you see
wanna keep
Louis,
going. Right.
Louis' house, you know.
Right. Now that's my cousin Boo, right? When you get to cousin Boo's house, you want to make a left.
Okay, yeah, that's exactly what it says on the compass. All
Right.
So what the manuals for using a compass know about this, and it's called an offset. So depending on where you are on Earth's surface, when you whip out the compass, you would put an angle offset to find out what true north is. But that changes depending on where you are on Earth's surface. So it's what I had an issue with is if you knew where you are on Earth's surface, you wouldn't need the
We need
compass.
the compass in the first place.
Mhm.
Absolutely.
In the first place.
That's like people say, I lost my keys. Well, where'd you leave them last? What? What? Well, what was the last place you left?
I left them on the counter.
Exactly. Like,
That is a stupid question, right?
that is crazy, right? But
You know, another
anyway.
stupid one is someone gets injured skiing and they got to be like hauled off to the hospital, and someone asks them, "Did that happen on your last run?"
Exactly.
Yes, of course it did.
No, you know, the thing is, I love excruciating pain and skiing. The pain enhances the skiing experience. So when my tibia is sticking out of my leg, that's when I want to get back on the chairlift.
All right,
So anyway,
So that's where that is. All right. So in the era of GPS, which knows exactly where the poles are and what the grid system is like, compasses are basically completely obsolete. Plus, if you know any astronomy, you'll know which way north is and which way the sun is pointing. I mean, so the compass, I think, is overrated in this regard, compared with other ways you can also find out where you are. But anyway, so that's Earth's magnetic field. It's relatively weak. Okay? It's weak. So if you take a bar magnet, I don't know if anyone still has them, you can do this, tie a string in the middle where it's balanced and just sort of suspend it there. It will slowly line up with Earth's magnetic field,
okay.
provided the string is twisty enough so that it can aim where it wants. It'll slowly line up, and the north is going to point north to Earth's south magnetic field. All right. It turns out, as weak ass as this field is, it's not always at the same strength, nor is it always oriented the same way. The magnetic pole of the Earth flips, and it has flipped many times.
Wow.
I don't know if anybody knew that.
That's
Don't know.
okay. This is good stuff, and now I'm really intrigued.
And 100% of the times of the occasions where people say, I hear the world is going to end and Earth's axis is going to flip, because they heard something about Earth's axis flipping,
Right.
and they think somehow Santa Claus is going to be south instead of north, when what they read about Earth's axis flipping has been entirely related to the magnetic field flipping.
Gotcha.
And not Earth
So the
flipping
Earth
over.
is not actually tumbling over
No.
so that top is bottom and bottom is top.
That has never happened.
That's
Correct.
never happened.
Correct.
What's happening is the actual magnetic field, which is the thing surrounding the Earth, that orientation changes.
Right, and it's not just the part of it we measure and see is outside of the Earth,
Right.
but it's generated from deep
From the
within
inside
core.
of the Earth.
I haven't gotten there yet, but I'm just saying that this can reduce in strength, come back in a reversed polarity, reduce in strength and come back again, and that flips. And this goes on every
All
half
right.
million years.
So now I got to know this.
What's that?
In that process, is it an equal diminishing so that it actually goes down to not being there at all, and then, or
We think so. Yeah. So what you have volcanic deposits that had metallic ingredients in it, and when the lava freezes, basically hits room temperature and freezes, it locks in the magnetic orientation of where that lava was at that time, and so people who study this can track the orientation of these magnetic rocks as they get. Yeah, brilliant. It's completely.
that is
brilliant.
insane.
Yes. Yes.
Oh my God, that's crazy.
Yes. Yes. Okay. So
I love it.
people wondered. By the way, we are shielded from harmful particles from the sun by this magnetic field. It gets channeled towards the magnetic poles, and it collides with the atmosphere and renders it aglow, and it creates the northern and southern lights, the aurora borealis and the aurora australis. Okay,
Earth's force
That-
field.
that is Earth's magnetic force field deflecting particles, and that's why they don't all go to Santa Claus. They go to the best shows are in this ring. It's called a ring. It's a highly luminous ring where you have the best action of this excited air molecules, and it's over Canada. Okay, and it's not. That's why we get better aurora borealis than they do over in Russia, because we have the pole over on our side, our North American side.
Finally, something good about Canada. Come
That
on,
and their health
Canada.
insurance. Okay,
Canada, you know we love you. You know
we love Canada. So, so it shields us from that. So now here's what's going on inside the core. You get a magnetic field when you have a fluid. In this case, it would be sort of molten magnetic materials, iron and nickel, in our core. All right, and if it's molten, it means you can move, you convect. There's movement within this material. We know from basic electromagnetism 101, if you move a charge, okay, you create a current. If you create a current, you create a magnetic field.
Right.
It's called a dynamo theory of magnetic fields. And this is
We do it in class. You take the copper wire.
the copper wire, you pass it through. Exactly.
pass it through.
And you
It's the
see the
same-
meter checks, and
Right.
the electricity and the magnetism go together. That's why it became one word.
Exactly.
Right? Early 1800s, I got electricity and I got magnetism. And you find out one is a manifestation of the other. We glued the words together and we made the word electromagnetism.
Sweet.
So, because of this, when you have a molten core of conductive materials, in our case it's metal, you can generate what's called a dynamo and sustain magnetic fields for millions of years.
Wow.
Okay, or a magnetic field phenomenon. So, and as the magnetic field lines get twisted, what happens is they can break and reconnect, and often when they reconnect, they have the opposite polarity than they had before. And that's what's
That's-
been going on Earth.
that's so cool.
Forever.
That's so cool.
And by the way, the sun's magnetic field goes through the sunspot cycle goes through an 11-year from peak to low, and sunspots always come in pairs. There's a positive and a negative because they're magnetic. I don't know if you knew that. They're magnetic pairs.
I did not know
sunspots.
that.
Okay, so now watch. Every 11 years, the sun's magnetic field flips, and when the sunspots show up again, they're now oppositely configured. So Earth is not the only thing whose magnetic field flips. It happens to the sun every 11 years. So this is not a new phenomenon. The understanding of it is relatively modern, late 20th century, mid to late 20th century. But there it is. That's our magnetic field. There was worries that when the field went to zero and switched, maybe all the bad particles would come and kill all life on Earth, and maybe the migrating animals.
That's when a portal to another dimension opens, and we're taken over by
That'd be a good story, right?
Yeah, it would be kind of cool,
when
right?
the magnetic field drops to zero, what happens next?
Yeah.
So what you do is you can look at what effect that would have. There are also many animals that it is asserted that they use the magnetic field particles in their brain to know which way north and south is as navigation to migrate. I've not been as convinced as others have been of that explanation, but let's even give it to them. Fine. You would wonder, will they not know how to fly, how to swim, how to migrate from one place to another, to get out of the cold climates in the winter and return in the summer? You look at the fossil record over those periods, and there's no meaningful extinction episodes happening over any of these.
Right.
So
Because-
whatever our worries are, life on Earth seems to survive them just fine.
Right. And everybody knows that birds don't really use the magnetic field. They use Google Bird Maps. And Google Bird Maps is, pretty dope, man.
Plus, they
dope.
can track you. That's how they know how to shit on your head. You see, Google targeting. Bombs away.
That's funny.
So there you have it. And my only issue with whether animals use magnetic fields is they don't. If the animal knows where the sun rises and sets, and there are other ways to know. Like I said, if you didn't have a compass, you still can figure it out. And so animals are always smarter than I think we give them credit
Absolutely.
for.
And the truth of the matter is, even we, as explorers and being out in the sea, we didn't use magnetic fields. We used the stars.
We use the stars. That's correct.
Right.
On a
So,
cloudy night, it's a little harder. You could crash into the rocks on a cloudy night, but on a clear night, you could use
Right,
the
exactly.
stars.
So yeah, all right, cool, man.
Yeah. So
Wow.
there you have it. That's Earth's magnetic field.
That's fun stuff. I love
And
it.
by the way, magnetism in general, you didn't ask this, but I'm putting it out there, is to understand it. We've known about magnets ever since lodestone was discovered, this rock that contained the iron that was magnetized before we isolated the iron from it. It's called lodestone. It's still called lodestone. There's no understanding of magnetic fields without quantum physics.
Okay, well then we don't understand magnetism. So sorry, guys.
No, speak your own damn self don't understand the magnet. So, no, you got to get down in there, and the electrons in orbit in their orbital clouds around their nuclei. There's a point where they align with adjacent atoms, and once that's aligned and coherent, you have a stable magnetic field.
Yeah,
and
but
there's
you could create a magnet. We used to do this. You take a pin, right? A little steel pin, and you take a magnet, and it doesn't even have to be a strong magnet, and you just stroke it. You keep stroking
Right, so
and
there you
stroking
go, and you're
stroking.
aligning all of those magnetic domains to
Right.
create a coherent magnet. Now there are other magnets where they'll only stay magnetized in the presence of an electric field, and you remove the electric field, then they demagnetize immediately. This is how you get electromagnets.
That's how the trains run.
Maybe I don't know enough about trains, but I do know that thing that picks up cars in the trash yard.
Oh, nice.
It grabs them by
I
their
love
roof
that thing.
and
I
picks them.
love
I'm not
that.
talking about the clamps, I'm talking about that.
No, the
that
big disc.
flat thing, the disc
Yeah,
thing.
that comes down and just
Right,
picks up the whole.
So you flip the switch, magnet on, boom, there it is. You bring it to the side, magnet off, and you can drop it. So that's an electromagnet, highly functional and exploitive of quantum physics.
Nice. Very
There
cool.
you go, Chuck. We ran out of time.
Wow, well, that was a good one, man. I think this talk will stick with me for a while.
Yeah, and Santa Claus.
That was a bad magnet joke. I'm sorry.
Okay. So I missed it. Sorry.
Yeah,
It'll
sorry,
stick with
man.
you.
I shouldn't have done that. I'm really embarrassed that I actually did that. I'm sorry.
I'm embarrassed I didn't catch it. No, you say this explainer will stick to me for a long time. I would have gotten it
For a
had you
long
said it
time.
would stick to
Right.
me. Oh, by the way, just one other thing. If you're between the North Pole, geographic pole, and the North geomagnetic pole, if you're
Right.
between those two, your compass will always point due south,
Oh wow,
right? Because
this damn thing is broken.
yep. That's all I'm saying.
Awesome.
There you go, Chuck. All right, we got to call it quits there. This has been another Star Talk Explainer video. Chuck, always good to have you.
Always a pleasure.
Neil deGrasse Tyson here. Keep looking. Okay.
So I love this guy so much. Also, he just gave you a total awesome preview about everything we're going to talk about for the next few minutes. All right. So One cool thing he didn't tell you about is what happens if you cut a magnet in half trying to separate the north and south seeking parts. So you can do this with a lodestone or a magnet. If you divide it in the middle, two new poles appear, giving each half a pair of opposite poles like the poles of the original magnet. It creates basically a new north and south pole on each piece. In fact, every piece created by repeatedly slicing the magnet will have exactly one north pole, one south pole, no matter how small you slice it, yes? This demonstrates that a magnetic pole is always paired with its opposite. Thus, every magnet is dipolar. And no exception to this rule has ever been found. So some theorists have imagined that isolated north poles and south poles, monopoles, occur somewhere in nature. But the evidence so far has not won general acceptance, though if you poke around on YouTube for about 4 seconds, you'll find a lot of very cool videos explaining why this is probably something that we haven't discovered yet, but will find someday. If you're interested, talk to me. I will show you them. So our observation of all these things leads us to formulate a law called the law of magnetic poles. And it's a really similar law to that governing the interaction between two electric charges. So basically, if we have two lodestones or magnets hanging close together, it reveals a force that exists between any two of their poles. And let's get a little video of this here.
Magnet, right? See? So they are repelling each other. North, repel. And south?
Ah, beautiful. So what do we say? North, repel. South, attract. A north pole and a south pole come together. Two north poles or two south poles avoid contact. Unlike poles attract, whereas like poles repel. If you forget, you can remember the Paula Abdul song. It works here perfectly. But just like Neil says, this is how our compass shows us that the North Pole is really the South Pole and our South Pole is really a north-seeking pole. So keep your eyes open for that. All right.
Magnet, right?
Oopsies. So let's talk about some types of magnets. Now, in order to know how easily a material will turn into a magnet, I know in the video he mentioned you can take a magnet and just stroke it with a needle and the needle will become magnetized. We really have to look at how strongly it responds to a magnet. So no material is entirely unresponsive. Even water is responsive. We're going to see that here. Every material is either attracted or repelled, though the response may be so feeble as to be basically undetectable under ordinary circumstances. At room temperature, the only materials that react significantly to the presence of a magnet are a few metals and their alloys. Iron and steel are strongly attracted. Cobalt, nickel, gadolinium, I'm going to say this so wrong, gadolinium and dysprosium are less strongly attracted. But check it out, even water will do a thing. Take a look.
Hey Magnet fans! This video is kind of a follow-up to Brainiac 75's awesome video about whether powerful magnets will attract to the iron in our blood. If you haven't seen it, you should definitely go check that out first. In his video, a small cup of blood was placed on a piece of styrofoam floating in a bucket of water. It's a great trick to show the weak diamagnetic forces from a strong magnet to the small cup of blood. The force is very tiny, but it does repel the little cup of blood just a tiny bit. While we were watching it, it occurred to us that the effect might not have anything to do with how hemoglobin reacts in a magnetic field. After all, blood's about 50% water. No matter how much that tiny amount of iron in red blood cells might react, you might still see the diamagnetic repelling action because a strong neodymium magnet repels water. There are a lot more water molecules in his cup of blood than iron molecules. Anyway, this short video shows the same kind of diamagnetic repulsion between a magnet and a cup of water.
Oh, come on, that's pretty cool now. All right. So let's talk about some temporary and permanent magnets. So although pure iron is among the easiest material to magnetize, it also demagnetizes as well. So iron magnets and other easily demagnetized magnets are therefore classified as temporary magnets. If a magnet must be capable of both gaining and rapidly losing magnetization, the best material is a permalloy, an alloy of nickel and iron in approximately a 3-to-1 ratio. Now we'll talk later about the different usages for this type of material. When it is turned north-south, a bar of permalloy will magnetize in Earth's magnetic field to attract iron filings, but instantly drops them when it's turned east-west. Magnets that retain their magnetization are classified as permanent magnets. Many permanent magnets are made of alnico, which is maybe my new favorite word. It's an alloy of aluminum, nickel, cobalt, and iron. Get it? Alnico and iron in various proportions. Other permanent magnets contain rare earth compounds of cobalt. That's fun. So making magnets, let's talk about magnetization. There's 2 main ways to make a magnet. Number 1, you can magnetize an object by stroking or touching it with an existing magnet, and that's called magnetization by contact. And again, he gave the example in the video of taking a needle and putting it against a magnet to seeing if you could magnetize it by contact. You have to do it like a bunch of times. If you are interested in doing this, pause the video and come talk to me right now. Otherwise, please continue. Magnetizing an object by bringing it into the presence of an existing magnet is called magnetization by induction. This will magnetize an object, but it'll magnetize it to a lesser extent. Now, if we can magnetize something, we also have to talk about demagnetizing it. So just as magnetic properties can be acquired, they can also be lost. An existing magnet can be demagnetized under several conditions, including heat, rough handling, and improper storage. Like poles have a weakening effect on each other, like a north to north or south to south. So when you put magnets away, they should be stacked in pairs with south to north and north to south, so they're not like butting against each other. It can also help to place a piece of soft iron, a keeper, it's called a keeper, across the poles. So sometimes you'll see those in between the U-shaped magnets. We have a couple of those, so you look around the room and you'll see them. Now I want to talk about Coulomb. Now we remember Coulomb from our last unit. Coulomb's law of magnetic force is a variation on Coulomb's law of electric force. When Coulomb adapted his torsion balance to the study of magnetic force, he discovered that magnetic force and electric force are governed by similar laws. You can see his torsion balance to the left. To be specific, magnetic force diminishes with the square of the distance between the 2 magnetic poles and increases with the product of their respective strength. Now I know you're thinking, but Donna, I have definitely heard you say those words to me before, and you'd be absolutely right. Take a peek. We have Coulomb's law of magnetic force on the left, that the force equals a constant of proportionality times the charges of the 2 poles divided by the distance between them. And on the right, we have Coulomb's law of electric force, which looks like the same darn thing, except for instead of it being the charges of the 2 poles, it is the charges of the point charges that we were using here. So they look pretty similar, invented by the same guy. So let's talk a little bit about these magnetic fields, if we're going to talk about the strength of them, yes? Since one magnetic pole exerts a force on another at a distance, again, we're thinking about this being mediated by a force field in between them. The first pole kind of alters the space surrounding it in such a way that the space itself impresses a force upon the second pole. The altered magnetic space is said to contain a magnetic field, which is, you can think about it in the same way as we think about an electric field, because as Neil deGrasse Tyson pointed out, they are essentially the same thing caused by the same stuff. So on diagrams or drawings, scientists often use these is kind of like imaginary, they're called lines of flux, to show, and again, imaginary, not that they're imaginary, like they don't exist. We actually do draw them in a very real way. They're imaginary because you can't actually see them in real life. And they show basically the same effect as we were thinking about when we were doing electric field out of a point charge. So much as we use lines of force when discussing electric charge, we're going to use the same thing here. A magnetic field is not confined, obviously, to the lines that are drawn. The magnetic field also exists between these lines. So please pause the video now and head to station 1, and you're going to get some kind of intuitive visuals of what this might look like. Okay, welcome back. Let's talk a little bit more about the requirements for mapping lines of flux. So when we're mapping the lines of flux, the direction of the field strength acting on an isolated north pole is tangent to the line of flux at every point. So what does that mean? Let's see if I can't take out my little pen here. That means if we have a force that's curved here, going like this, if that's our force going like that, or our line of flux rather, that if we have a point that's right here, draw a line that's tangent to the curve and in the same direction, and that's going to be how, if you just dropped off a charge right there, where it would be pushed to. And so it'll be pushed in a straight line tangent to the line of flux. So each line of flux shows the path that would be taken if an isolated north pole, if it were placed somewhere along this line and restricted to gradual motion. Rule number 2, lines of flux must be drawn as closed loops. Theoretically, if there wasn't a bar in the way, these things would just keep looping in on themselves. So in this figure here to the right, you'll notice that every line of flux associated with a bar magnet goes from the north to the south. This is similar to the electric fields that come out of the positive charge and into the negative charge. So we have similar rules for magnets. An isolated north pole placed in a line of flux would, if it were able to pass through the body of the magnet, travel indefinitely around in a looping path marked by these lines. So when unlike poles of two magnets are positioned close together, the lines of flux bridge the gap between the magnets. It'll go from one to the other. But when the poles of two magnets are positioned close together, the loops, when they are of the same, when two like magnets are positioned close together, the loops appear to be repelled by the loops of the other. So you can see the like poles in the figure on the left, figure A, and the unlike poles, English Donna, unlike poles on the left, where the lines seem to go straight across, and the like poles that repel each other on the right, they look like kind of like they're bouncing off of each other. Number 3, the lines of flux are more concentrated where the magnetic field is stronger. So we saw that in our video the other day with electric field strength. Same for magnetic field strength, because essentially they are the same thing. The lines of flux are drawn perpendicular to the surface of the magnet, which means, again, if you're looking at the magnet surface here, if it's like a flat surface, the lines of flux come out of it at a 90-degree angle. So we're going to keep an eye on that as well, because that'll give you a hint as to which direction they should point as they pop out of the magnet. And the number of lines must be proportional to the average field strength upon that surface. So for example, if you double the force, you have to double the number of field lines that are coming from that area of the magnet. All right. Field strength of a magnetic field is termed magnetic induction. We call it magnetic induction. Magnetic induction is symbolized by a capital B and is commonly measured in Teslas, which is noted by a capital T. Now, when you do it right, the proliferation you can make from all the different kinds of different magnets looks really, really cool. You see a bar magnet here, you see a disc magnet, and you'll get a chance to do that a little bit later. But before we do, let's talk a little bit about permeability. So permeability is the extent to which a material absorbs and concentrates lines of flux. Basically, permeability is how strongly something can be magnetized by a magnetic field. Iron and other materials used to make magnets have the greatest tendency to absorb the lines of flux. Please pause the video here and head to station 2, and you're going to notice something pretty cool about permeability. All right, now that you're back, I'll spoil everything. A magnetic field easily penetrates a non-permeable material such as a barrier of wood or glass or plastic or paper or any of the other things that you had over there at your station. A strong magnet, like if you have a magnet that's strong enough and it's resting on a board, it'll lift a paper clip to the bottom of the board straight through the wooden board. But the same magnet resting on the bottom of a steel can has no effect on the paper clip below the can, even though in this instant the paper clip is separated from the magnet by a thinner barrier. This occurs because whereas the wood is non-permeable, meaning it doesn't absorb the lines of flux, steel is highly permeable. Thus, the magnetic field that originates within the can, even if the poles are reversed, it gets absorbed by the steel. So instead of penetrating the bottom, the lines of flux make their way from pole to pole along the most direct route through the can, as you can see in the picture here. So let's talk about this fun fact called a magnetic moment. So let's ask ourselves, why should magnetic force have a strong effect on some materials like iron, but hardly any effect on other materials like glass? Well, what's the difference between them? Well, it's their atoms. The atoms have something to do with it that make up the material. So protons and neutrons are cool, but we know they don't move around much. We want to keep an eye on the electron. So every magnetic force arises from a charge in motion, just like Neil deGrasse Tyson was talking about the magnetic forces and the electric forces are really just the electromagnetic force. So what is a magnetic moment? A magnetic moment is a measure of how strongly something produces a magnetic field and in which direction that field points. So in an atom, magnetic moment comes from mainly the electrons, and there are two key things that the electrons do that contribute to this. Number one, electron spin. So electrons don't actually spin. They do things that it's a quantum property, like Neil deGrasse Tyson was saying, that gives it angular momentum and a magnetic field. So it's kind of like spinning in that it gives a spinning vibe. But when it does that, they act almost as if they're a tiny little bar magnet. When we talk a little bit about current and how current produces a magnetic field, this will make a little bit more sense too, so I'll reference it then as well. But that's one thing, the electron spin. Another thing is the orbital motion of electrons. Now, electrons move in orbitals around the nucleus. Again, hear me when I say this, they don't orbit like planets around the nucleus. We know from chemistry that they exist in their orbitals. But since they are charged and in motion in those orbitals, it creates a current, which is like a tiny loop of wire. Again, we'll come back to this when we talk about current, which also generates a magnetic field. There's also that which is called the domain theory. And the domain theory means that we have groups of atoms with unpaired electrons, and they turn one by one until they align with the magnetic field. And when an external magnetic field is introduced, the domains align with the field and they begin to force neighboring domains into alignment. And if the field is strong enough, the spin axes of all the unpaired electrons will point in the same direction, and this condition is called saturation. So you can see that picture on the left. We got all the little domains of atoms all willy-nilly pointing in all kinds of directions. But when we bring a magnet into the situation, a magnetic field into the situation, it will align the domains and the material becomes magnetic. We got our lovely friend here who's going to tell us all kinds of interesting things about it. Please enjoy. No notes to take.
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 21. It's on the magnetic dipole moment, which is the torque that material experiences when you put it in a magnetic field. And so if you add an object to a magnetic field and it's not affected, then it doesn't have this magnetic dipole moment. And so let's say we take a bar magnet like this. Is it magnetized? Well, a quick way to figure that out is to use a compass. And so a compass is essentially a small floating magnet on a needle. And so if we put this next to the bar magnet, you can see that the south side of the compass is facing the north side of the magnet, and vice versa down here on the other side of the magnet. So we would say it's definitely magnetized. And it's the magnetic dipole moment inside the bar magnet that's causing it to be magnetized. But let's say I want to break this magnet, and I just crack it in half. Have I destroyed the magnet? Well, we'd test it in the same way. We'd use compasses again at either side, and you can see that they line up. In this case, the north side of this magnet is facing the south side of the smaller magnet. And so now we've essentially created two dipoles. And if you break it in half again, we have two smaller magnets, and you can keep breaking it and breaking it and breaking it. And what you'll find is you'll just make smaller and smaller and smaller magnets. And so there's something intrinsic in the magnet itself that's causing it to be magnetized, and that's the magnetic dipole moment. And so matter that shows a magnetic behavior has this property called the magnetic dipole moment. And so it could be at the level of domains, they're really small parts of a magnet. They can be up to about the size of a millimeter. But if we break down those, they're built up of atoms, and atoms themselves are made up of electrons. And the spin of those electrons gives them a magnetic dipole moment as well. And so all of these levels of dipoles is creating the overall effect of a magnet. And so what is magnetism? Well, in a permanent magnet or an induced magnet, what we're doing is lining up those dipoles, and now the whole object has a dipole as well, a north and a south. And so to understand what a dipole is, it simply means two charges. And so if we were to look at an electric dipole, right here we have a positive charge and a negative charge, and then we have electric fields that form around the outside of it. So this is an electric dipole. Watch how this diagram changes as I move it to a magnetized dipole, and you'll see that it really didn't change at all. Now we've got a north and a south, and instead of having an electric field, we have a magnetic field. And so what is a magnetic dipole? It's simply a dipole, two charges, but those are magnetized. And so if we were to look at a bar magnet like this, it has a north and a south side. But what really is creating it are these domains inside the magnet itself. And so iron, for example, that's not magnetized, what we would find is inside those domains, the dipoles are there, but they're facing in every other direction. And so if I were to change this and make it a permanent magnet, watch what happens to those domains is they all essentially line up. And so it's the domains that must be causing the magnetism. Well, it's not. It could be the atoms as well. So if we look at the atoms themselves, those are made up of charges, and so those can have dipoles. And even if we get to the level of electrons, because of their spin, are magnetized as well. And so at all levels through in the magnet, we can see these dipoles, and those are contributing to the overall behavior of the magnet itself. And so what is a permanent magnet? It's essentially material that can permanently create these magnetic fields. And so if you ever add it to another magnetic field, it'll experience a torque or a moment based on those magnetic dipoles. And so does all material on our planet have the ability to be magnetized? No, it's based on the internal atomic and molecular structure. But if I were to take paper clips, for example, put them next to a permanent magnet, they could be an induced magnet. In other words, all those domains are starting to line up, and then you would have a paper clip that is an induced magnet. And so it's only a few of the elements on the periodic table that can be lined up like this, being ferromagnetic. So it could be iron, copper, nickel. And then we have these rare earth metals like a neodymium magnet that we have right here, and it has this ferrofluid over the surface of it. You can almost see those magnetic fields coming out of that magnet. And so did you learn that a magnet is created through these magnetic dipole moments that occur at all different levels inside the structure of the magnet? I hope so, and I hope that was helpful.
Super helpful. Thank you. All right. So now let's talk about something really cool called the Curie point. So talk about how to magnetize and demagnetize, magnetize. Now this is how to demagnetize something. We mentioned that a magnet can lose its magnetization when it's heated up. So basically we know what heat does. Heat makes the molecules move faster and more erratically. So the heat basically shakes up the atomic dipoles out of their strict parallel alignment, causing the reemergence of separate, more disorganized domains, right? The temperature that is high enough to disturb the domains of a substance is called the Curie point. Above that temperature, about 770 degrees Celsius for iron, the material changes from strongly attracted to weakly attracted. Let's see that in action.
Hi gang, here's a fun short science video demonstrating the Curie temperature, or Curie point, using this neat little heat engine. This black thing at the end of this copper wire is a piece of nickel metal. It's attracted to this area by these powerful magnets. But that puts it in the candle flame. Once the nickel gets hot enough, it's no longer attracted to the magnets and falls away, where it can cool off. Once it's cooled enough, it's attracted back to the magnets, and the whole thing repeats. How does it work? Like all materials, the piece of nickel metal is made up of atoms. The atoms it's made of act as tiny magnets, mostly due to electron spin. But we'll just think of the whole atoms as magnets. Another term for these tiny magnets is dipoles. In nickel, these tiny dipoles are grouped into domains. Each domain is a group of tiny magnets, all pointing in the same direction. But notice that the magnets of different domains point in different directions. That's why nickel doesn't normally act like a magnet. But when we put it in the magnetic field of a permanent magnet, the atoms in the domains now point in the same direction, lining up with the magnetic field. Now the nickel behaves like a magnet as a whole and is attracted to our permanent magnet. We call a material that behaves like this a ferromagnetic material. But that pulls it into the candle flame that heats up the atoms in the nickel. What that means is that the atoms start to move around randomly, but they still stay lined up with the magnetic field. And at a certain temperature, called the Curie temperature, the tiny magnets all of a sudden all point in different directions. They aren't even grouped into domains anymore, and so it no longer acts like a magnet and falls away. Until it cools again and the tiny magnets line up with the magnetic field again. Here's how I made it. To start with, I needed some nickel. I could have used other materials instead, like iron, but iron has a Curie temperature of 770 Celsius, or 1418 Fahrenheit. For nickel, the Curie temperature is only 358 Celsius, or 676 Fahrenheit, much quicker to heat up. Often people use nickel wire for this, but I didn't have any. Luckily, Canadian quarters made between 1968 and 1999 are 99.9% nickel. And looking in a roll of them I had, I found one from 1974. I started by drilling some holes in it. A whole quarter would have taken too long to heat up and then cool down, so I cut out a small piece. I then attached some wire to it. For the powerful magnets, I had these two neodymium magnets, taken from a computer hard drive. A quick test shows that the nickel is attracted to the magnets. But when I heat it above the Curie temperature, it's no longer attracted, until it cools down and is attracted again. I hung the wire from a screw and did some testing to figure out rough spacing for things. Next, I assembled this metal and wood structure out of scraps. To hold the screw in place, I put some more magnets, one on either side of this piece of aluminum, and used them to hold the screw in place. I then did something similar with the hard drive magnets. The nice thing about this setup is that it's all easily adjustable. I lit the candle, put it in place, and started adjusting things. And in no time at all, I got it working. Well, thanks for watching. See my YouTube channel, rims.org, for wires a piece of...
So fun, right? Come on, it's science in action. All right, let's talk about classifying different materials. These are some words you gotta know if you're gonna be thinking about magnets. First of all, we have diamagnetic. Diamagnetic is a material as a whole that is repelled by a magnet. Basically, the orbital magnets are repelled by an external magnet. Examples of this would be copper, mercury, sodium chloride, gold, lead, and the noble gases. This is because their electrons are all paired. Faraday discovered that some materials are repelled by a magnet as he worked with bismuth, the most diamagnetic material at room temperature. Think D doesn't attract. Next material we want to talk about are paramagnetic materials. If we say something is paramagnetic, it means it has one or more unpaired electrons for each atom, and then it will be weakly attracted to an external magnet. Some examples would be aluminum, oxygen, and wood. You could think paramagnetic, pairs together. Now we also have my personal favorite, ferromagnetic, which means strongly attracted to a magnet because it has two or more unpaired electrons. Some examples would be iron, the leading ferromagnetic material, because it has 4 unpaired electrons in its third shell, accounting for the unusual magnetic properties of this metal. Cobalt and nickel are similarly structured, so they are similarly ferromagnetic. Think ferociously strong. Now, please, if you would, pause the video and answer these questions. Okay.